Sir, our live stream is ready.
Okay.
And Shyam, I'm going for a broadcast now.
Okay.
And Dr. Gunasekharan will start introducing. Sir?
Okay, sir. Okay.
Gunasekharan sir, now broadcast na press panna poren. So
okay, sir.
Get ready. Okay, I'm going to start the broadcast.
Okay.
Just wait for the attendees to join. Sir, our live stream is ready.
Okay.
And Shyam?
Yep.
Okay, sir. Broadcast is on.
Okay.
Okay. So I'll just wait for attendees to join.
Yeah, we can wait for a while.
Okay. Just 1 minute, I will wait.
Yeah.
Okay, Praveen, can I start, Praveen?
Yeah, you can start now.
Okay. Good morning, one and all. I am Dr. Gunasekharan, Assistant Professor in Department of Material Science, Central University of Tamil Nadu. Today is our third day of international webinar in recent advances in material science. I welcome all of you to our international webinar. Today, Dr. Shyam G. Krishnan with us as an invited speaker for this webinar session. First of all, I welcome Dr. Shyam Krishnan and extend our heartfelt thanks for giving this his valuable time for this webinar. Now, let me introduce Dr. Shyam Krishnan. Dr. Shyam Krishnan has completed his PhD from University Malaysia, for Pahang. He is having 10 years of teaching experience as a lecturer and also postgraduate teacher in various institutes, and presently working as a research fellow in Graphene and Advanced 2D Materials Research Group, Sunway University, Malaysia. His research interests involve the synthesis of energy storage materials for battery type supercapacitors and lithium-ion batteries. Currently, his research study focuses on the modification of the charge storage properties and increasing the cycling stability of the mentioned ternary metal cobaltites by reduced graphene oxide, graphene modification. His planned future research will focus on the synthesis of controlled magnesium-based cobalt nanowires, as well as porous carbon from natural resources for flexible energy storage devices. So this is the short introduction about the speaker, Dr. Shyam G. Krishnan. Dr. Shyam, please take care of this session, please.
Okay. Thank you, Dr. Gunasekharan, for wonderful words about me. Hi, all. I am Dr. Shyam, working in Sunway Group, especially in Graphene and Advanced 2D Materials Research Group. Today, I am going to present a topic, is a general topic, I should say, that what are the recent research trends on the materials for supercapacitor as well as supercap-battery. So initially, from a layman's point of view, I'll be having 3, 4, or 5 or 6 slides for all of us to understand what's the difference between a supercapacitor as well as supercap-battery, but which is a new term which has been emerged as a result of variation in charge storage processes. So firstly, we should understand where our energy storage is been, or energy storage market is been standing. 3 sorts of devices. We can say 3 sorts of energy storage devices like capacitors, then supercapacitors as well as batteries. They own the prime space of energy storage market, and 2 important factors concerning these 2 devices are its energy density as well as power density. Am I audible? Am I audible?
Yes, Dr. Shyam.
Yeah, okay, fine. So there are two questions related with these energy storage devices. Is that how fast it can be charged or discharged, and how much energy the device can store. That's its power density as well as energy density respectively. And concerning these devices, when we say that capacitors, they are really the power devices, we say that for power applications we give capacitors whose power density will be very high, but its energy density will be very less. And battery whose energy density will be very high, but power density will be very less. And there is a gap between the capacitors as well as batteries, which will be filled with the use of supercapacitors. This was the initial research trend for what we can say supercapacitors. So the research idea behind designing the material of supercapacitor was to improve the energy density without compromising its power density. So again, we see that there is a what zigzag between capacitors as well as battery, and we can say that the fulcrum of this zigzag can be designed with respect to a supercapacitor. So initially, we should be able to understand what's a capacitor. That means if two conductors are there, and if we apply a potential difference between these two conductors, then definitely the charges are going to separate. So that one will be having enough positive charges and another will be having negative charges, where sometimes saturations can happen, so that again the inverse process will take place, so that we can say that charging as well as discharging will be taking place with respect to one another this thing. So usually in smaller classes as well as we have defined capacitance as the ratio of electric charge on each conductor to the potential difference between them. And we already will be having a small idea that energy here, it is stored as a charge separation via an insulating dielectric. And the equation for capacitance, that means the general equation for capacitance is simply defined as epsilon 0 A by D. So in that A will be the area of the plate, as well as D is the difference between the two conductor. So C can be increased by increasing the area and reducing the separation between the two plates. So that's the basic idea of increasing the capacitance of a capacitor. Then comes to the term regarding supercapacitor. So generally the question is that what is super in a supercapacitor? So as we say that capacitor is there and supercapacitor is there, usually a normal question arises in all of us is that what is super in this supercapacitor? So in that process, so in supercapacitor, we say that there is no redox reaction involved in the storage of charges, where in a capacitor, especially in an electrolytic capacitor, we say that there is a charge is being stored using redox process. Then here in this thing, thicker surfaces are we can say electrodes, and thinner dielectrics will be there. Then it will be having lower series equivalent series resistance. Then it will be having higher power density, lower charging time, as well as higher cycle life. And it can operate. That's a basic advantage of the supercapacitor compared to a battery, is the working of various temperature range. Then this is what the schematical diagram of this supercapacitor working, that we already see that there are three requirements for a supercapacitor, especially for an electric double layer capacitor. or normally we call this electric double layer capacitor as a supercapacitor. Why? Because here it consists of an electrolyte, then an electrode, then a separator. Normally it will be a paper separator soaked in electrolyte. So in that this thing, what we are observing is that when we are applying a potential difference, then these charges will be accumulated on both sides of the electrode, like negative as well as positive, so that there is a simple accumulation of charges near the surfaces as well as a little bit inside the surfaces of the electrode, so that there will be a double layer will be formed in that particular region, and that's why we are calling it as electric double layer capacitor. Then another sort of capacitor is there that also comes under the category of the supercapacitor, that we call it as a pseudo-capacitor. That means the material like ruthenium oxide, manganese oxide, etc. are having the property of a little bit further interaction to the electrode surface. Electrolyte ions can intercalate little bit higher into the pores of the electrode material, so that Faradic reactions as well as redox reaction will be involved in pseudo-capacitor, whereas in EDLC there is no redox process will be involved. So while looking at the material, especially for pseudo-capacitors, usually ruthenium oxide will be used as the material for this pseudo-capacitor, we say, so that there will be an electrolyte intercalation will be involved. But that involvement will be very fast, so that we call it as a Faradic or Faradic process. Then the energy storage process will be almost similar to EDLC, where a double layer will be formed between electrode as well as electrolyte interface. But here the difference compared to a normal supercapacitor or an EDLC with supercapacitor is that electrolyte ions can move deeper into the pores, and there will be a reversible redox reaction will be involved. So as a result, more amount of active material will be involved for the reaction, so that its capacitance as well as energy density will be improved, but at the cost of lower power density. Why lower power density in this pseudo capacitor is because of the response time. Here, as the electrode will, the electrolyte ion will be moving into the pores of the electrode, it will be taking little bit more time, so that the response time for the charge storage will be a little bit higher, which will lower its power density. Then again, the reversibility of this charge storage is also what we can say. Sorry. Then the reversibility of the charge storage is also superior, measuring instantaneous capacitance in each interval. Some examples for the pseudo-capacitor materials are this doped carbon, ruthenium oxide, manganese oxide, etc. Then comes to the supercap-battery or battery type electrodes. So I am just going to explain this particular concept just based on the characterization technique of the electrode, that is cyclic voltammetry as well as charge discharge cycle. When we observe the cyclic voltammetry of a normal supercapacitor electrode, what we are seeing is that it's almost a rectangular shape CV it's coming. In that case, if we are taking instantaneous capacitance at each case, that instantaneous capacitance will be remaining the same, and the average capacitance will be the sum of the instantaneous capacitance for this particular supercapacitor electrode. For example, activated carbon or manganese oxide or ruthenium oxide all comes under this supercapacitor field. But in this battery type electrodes, what we are observing is that here this particular region, this region is blank. And here the charges will be stored like this. That means here in this there is no positive region. Here only here there is a negative region. So instead of this that means the instantaneous capacitance at this region will be different compared to this region. So we cannot take the capacitance as the sum of instantaneous capacitance, but instead of that, we will be taking an average value and reporting this as specific capacitance, which is not true. So that's why this particular term has arisen like supercap-battery, which is almost having battery type behavior, which is also measuring this what capacitive nature of that particular electrode. That's why that particular term called supercap-battery has come. And again, the thing is that the energy density of this particular material is not higher compared to the battery material, but it's more higher compared to a pseudo-capacitive or an EDLC material. That's why it's this particular term, a new term called supercap-battery came. So in that supercap-battery material, what we can observe will be a deeper electrolyte intercalation. Then similar energy storage process compared to pseudo-capacitance. Then electrolyte ions can move deeper into the pores than pseudo-capacitance. Improved capacitance, energy density, but lower power density. Reversibility of the charge storage is also lower the measuring the average capacitance than the instantaneous one. Then the basic materials for the supercap-battery material are metal oxides. That means usually transition metal oxides, we say, then transition metal chalcogenides, then MXene, metallic organic frameworks, etc. comes under this this particular field. Then the basic advantage of the supercap-battery material, as I explained earlier, is of its higher capacitance than energy density, but it all comes with a lower power density compared to pseudo-capacitors. Then in the supercapacitors itself, that means when we manufacture a supercapacitor, there are two types of supercapacitors. One is a symmetric one and another will be an asymmetric one. We usually call it as also called by the term called battery supercapacitor hybrid. So in that case, what it will be is that the cathode and anode, if both materials will be of same, especially both are of EDLC material, then we usually call it a symmetric supercapacitor. And almost all the supercapacitors available, commercial supercapacitors available in the market are of the symmetric type, where usually the cathode as well as anode will be made up of EDLC material, and lower number of electrons number will be accessed per unit surface area, we can say, and it will be having low energy density, high power density, as well as high cycling stability. Then compared to that, asymmetric supercapacitor will be having anode as well as cathode materials, different anode as well as cathode material, as well as it will be having this Faraday's charge transfer process, and the number of electrons involved per accessible surface area will be higher, as well as the high energy density power will be higher, but the power density will be lower. And the important problem regarding the asymmetric battery hybrid is its lower cycling stability compared to symmetric capacitor. So in that case, that means almost what we are observing is that almost 100 times cycling stability is lower compared to this symmetric one. Then for the supercapacitor electrode material, especially for EDLC, supercap-battery, etc., we are having some basic criteria for the material that are high surface area, which are the requirement for both the EDLC as well as supercap-battery material, and it's for larger electrode-electrolyte interface availability. Both high surface area is required. Similarly, high electrical conductivity is also required for fast charge discharge transfer. Then it will be having multiple oxidation state for supercap-battery material to achieve high capacitance, and it will be having high electrochemical reversibility for long cycle life. Then if we look at the materials which are available for supercapacitor, what we will be finding is that especially transition metal oxides are dominating the process, where ruthenium oxide and manganese oxide, as I have explained, that it comes under this what we can say super capacitor material. But the other material, other transition material like copper oxide, nickel oxide, cobalt oxide, all come under the supercapacitor materials realm. So the theoretical capacitance, as we are observing, is higher for cobalt oxide compared to these materials. But when comparing to the achieved capacitance, cobalt oxide, the other materials have achieved only lesser, what we can say, lesser achieved capacitance. Then while comparing its conductivity, the conductivity of ruthenium oxide is much more improved compared to other materials, and that's why they are being used as a pseudo-capacity material. But the factor which is hindering for its commercialization of ruthenium oxide is its availability. That means in Earth's crust, the availability of ruthenium oxide is very less compared to the other materials. So we always we know that the availability of the material decreases the cost of any particular technique. For example, when a mobile phone was launched, then it was launched at very higher prices, as well as the call rate also was very much higher. When almost everyone started using it, the call rate also dropped, as well as the mobile phone quality increased, as well as its price also decreased. Similarly, here the ruthenium oxide not be used for commercial purpose because its availability is lower. So that's as its availability is lower, then its price definitely will be higher. So the scientists have to look for alternative material rather than this ruthenium oxide as well as manganese oxide. Manganese oxide, as we know, that even if manganese oxide can be easily available, but while comparing to the conductivity of other materials, manganese oxide's conductivity is very less, even though it's having 7 oxidation states. What we are observing is that as its conductivity is lesser, the theoretical capacitance of manganese oxide also will be lower. So definitely there are another what we can say, another digging for this another source of materials, and another material which came is this of ternary metal cobaltates. That means replacement of one of the cobalt atom by another materials like nickel, manganese, copper, as well as zinc, produce these ternary metal cobaltates. And compared to the theoretical capacitance, these materials were having as much as higher theoretical capacitance compared to its parent compound. Here, why this cobalt oxide is not commercialized that much? Because of its toxicity. Then while comparing its achieved capacitance, that means these ternary metal cobaltates are achieving more capacitance than its parent compound. And while comparing the electrical conductivity, definitely the other materials like nickel cobaltate, manganese cobaltate, as well as copper cobaltate are having higher electrical conductivity. That means an order or 2 orders of electrical conductivity higher than this cobalt oxide. So that another sort of hot materials which came to this particular supercapacitor realm was this ternary metal cobaltates. And recently, it's our research group only explored the utility of this magnesium cobaltate, whose theoretical capacitance also was at as far as compared to this, as well as its conductivity. And we explored some of its utility, and we were the first, I think, research group whose findings were they reported for the utility of magnesium cobaltate as a supercapacitor material. Then compared to all these sorts of materials, when we say about EDLC, the most preferred materials are carbons. So now the present researchers are going on the synthesis of this bio-waste carbon, and these activated carbons synthesized from bio-waste are having the pretty advantage is that the precursors are bio-waste, so it's really and easily available. So, and the synthesis process is very simple. That means any sorts of research lab can synthesize this activated carbon. That means using one step or this thing two-step process. And usually the activated carbon, that means using chemical activation or physical activation, the carbons which we are getting will be having a higher surface area as well as proper porosity. And in this bio-waste carbon, the basic research for the supercapacitor application will be tuning its porosity. That means the correct porous structure is required for this material to have proper intercalation with electrolyte ions. So with that bio-waste, that means usually the capacity or the capacitance range for this activated carbon will be from 100 to 150 farad per gram. But tuning the porosity of this bio-waste carbon, they what the maximum capacitance was achieved is around 400 farad per gram. That means the carbonization temperature as well as washing process determine the utility of this bio-waste carbon for this supercapacitor application. In this bio-waste carbon itself, this carbon nanospheres now are the hot carbon materials for this supercapacitor application, owing to its appropriate pore size for this electrolyte intercalation. Then another sort of research which is going on in this bio-waste carbon is doping carbon with metal oxides, so that some amount of pseudo-capacitive property also can be clubbed together with this EDLC material, so that its energy density can be increased without much loss in its power density. Then one more technique in synthesizing this bio-waste carbons is this hydrothermal carbonization, which directly could produce this carbon nanospheres. One recent research which reported in 2019 synthesized this gold decorated bio-waste carbon nanospheres. So in that we can see is that a simple bio-waste leaf. In that simple bio-waste leaf, it's what in a short span of time we can produce this gold decorated material. And in that this thing, what we are observing is that here it's a cyclic voltammetry. It's almost what we can say that it's supercapacitor only. That much variation regarding that supercapacitor what nature it's not going, but definitely its capacitance, when we are seeing its capacitance from this CD curve can be calculated by charging, that means discharging time to charging time, that will be its Coulombic efficiency. And this by calculating the discharging time easily, we can calculate the specific capacitance. And what we can observe is that it's reaching around 300 to 400 this thing. And even this NICU spot, when we are observing this gold decorated this thing, that means if this particular shift is towards y-axis, we usually say that capacitive property of the material is increasing. That means the resistive nature of this particular material is decreasing. That means here this is one of the recent researches where they just added some gold precursor into this particular activity, what carbonize during this carbonization technique, they have synthesized this gold decorated carbon nanosphere, which have given very what we can say improved result. Similar sorts of researches are going on. So the purpose is like that. The main purpose of this research that we have to take care is that lower the cost also should be lower, as well as the scalability of the material should be high. If that both are coming as good, then only we can say that our research is meaning to be commercialized with respect to the industrial needs. Then another material, this is another hot material, we can say that it's another hot material for this particular supercapacitive realm, that is graphene and its composites. In that this thing graphene, we know that it's material which is having a higher surface area as well as higher conductivity, and its basic problem is that the accessibility of electrolyte ions to this much higher surface area. So again, the advantage of this graphene is that it's superior electrical conductivity. Then apart from superior electrical conductivity, its mechanical properties and extensive surface area. Then again, another advantage is that with pore size, its surface area is not changing. So then again, for energy storage application, another added advantage is both sides of the material could be easily accessed by electrolyte ions. Then higher surface area, as I explained earlier. Then basic research area of this particular graphene and its composite is to how to improve the accessible surface area of graphene for supercapacitor application. Then usually for improving the accessible surface area, the researches which are going on is this one. That means for this thing, a graphene nano composites with this thing, it is been formed, which can definitely improve the accessible surface area, and this graphene can help this particular nano composites with its higher electrical conductivity. So this is what this is sorry. Yeah, this is what a research which is showing that carbon nanotubes, they are doing this thing, two approaches, like that we know that there are two sorts of approaches for synthesizing this graphene, like that top to bottom as well as bottom to top approaches are there. In that, after synthesizing the graphene, that's when a research paper which came in 2011, they are discussing that if carbon nanotubes are intercalating into the layers of this graphene nano sheets, then it's giving more accessible surface area to this particular electrolyte ions, thereby improving the capacitance of this graphene material. But the beauty of the research is that another group have reported that this addition of carbon nanotubes to this graphene oxide do not improve this capacitance at all of this graphene material. Why? Because they are saying that only average capacitance value is increasing, and not the capacitance value of graphene could be increased by the addition of this carbon nanotube. Like that, plenty of research, what we can say, problems are there in graphene if we find. Then another material, that means another source of research which are been going on is just what we can say, it's just like decorating this graphene with some another pseudo-capacity material like MnO2, thereby increasing its what we can say capacitance as well as energy density. Similarly, another sort of this thing, it's like by making a polymer nano composite of this graphene to improve its energy storage parameters. This was another sort of research which was been published in 2013. And when we compare these are the results of this particular graphene zirconium oxide polymer nano composite. But in this case, when we look at it, the CV, what we are observing is that some redox peaks are being formed in the sorts of this thing. That means from the normal supercapacity behavior, this particular material is slowly changing to a battery type material. So here we cannot take the average capacitance. We should take, we cannot take instantaneous capacitance. We should take average capacitance, so that this material could be considered as a supercapacitor material rather than a supercapacitor material. So this is how the researches in this supercapacitor material is now progressing. Then another sort of materials which are largely used and are largely cited also for pseudo-capacitor as well pseudo-capacitor applications are these transition metal oxides. Then in transition metal oxides, especially like ruthenium oxide as well as manganese oxide. In this thing also, what we can observe is that the CV shape is almost rectangular, and almost there are what we can say that not that much Faraday reaction or redox reaction is happening in this particular material, so that the charge as well as discharge curve is also what we can say identical shape, so that this particular material can be considered as a pseudo capacitor material. And these material are selected because of these factors, because they are having high electrical conductivity, different oxidation states, high theoretical capacitance, and high electrochemical reversibility. Then our research group that was working on, where I completed my PhD, we were working in so much on this electrospinning techniques, so that we were synthesizing nano wires. The problem as well, there is one advantage with nano wire is that it's electron transport will be very smooth. But even though its electron transport will be very smooth, this nanowires active surface area will be very less. So the available surface area for the reaction, that means for redox reaction, will be very less. And these are the research reports which we published in 2014. And this also, as I explained, we published this particular result as supercapacitor material. But no longer it can be considered as a supercapacitor material because of the problem which I explained earlier. So this material can be considered as a supercapacitor material, where this nickel oxide nano wires were synthesized. Similarly, we synthesized one cobalt oxide nanowires also through the same synthesis technique. That means here we adopted a green synthesis technique, where in electrospinning some harmful chemicals were there, which can affect pollution and other problems, which can create pollution and other problems. So that here a green electrospinning technique was being employed, and this one actually was giving very much higher capacitance compared to other materials, because of the what we can say, because of the easy ion transport between the electrode as well as electrolyte interface, whose resistance, that means characteristic resistance of this particular material, were lower compared to other, as well as its performance also was comparable to any other what we can say, this asymmetric supercapacitor device. That means here we fabricated an asymmetric supercapacitor also. And we have determined that this cobalt oxide can also be a potential material for this particular supercapacitor or asymmetric supercapacitor or a battery supercapacitor hybrid material. Then our research again focused, rather than this ternary metal cobaltates, we focused on this thing, rather than on this cobalt oxide, we focused on this ternary metal cobaltates, where we tried to substitute one of the cobalt atom from the ternary sites of this particular material with materials like manganese, cobalt, zinc, magnesium, as well as iron. And as its theoretical capacitance, redox states, as well as conductivity and spinel structure, spinel structure could improve the result of this thing. An example for this thing, improved performance of this nickel oxide is the synthesis of this material from metallic or organic frameworks. So in this metallic, it's a very nice work which has been published in Advanced Energy Materials in 2017, which consider that this ion exchange etching as well could produce this hollow porous nickel cobaltate material, which will be used for these flexible devices. So another research trend which are going in this supercap-battery research field is in synthesizing these flexible wearable electronic devices. So for flexible wearable electronic devices, we should be having a flexible energy storage device. So in that case, this research reports the utility of nickel cobaltate. Then for this thing, we also have synthesized several magnesium cobalt oxide nanostructures through simple hydrothermal technique, and several morphologies like cuboidal microcrystals, like nanoflowers, nanospheres. We synthesized different materials, and what we have observed is that these materials are also having some utility for what we can say for this supercap-battery research. Then another material, this is another interesting material, that's metal dichalcogenides, again, which is having a layered structure. And the most explored this metal dichalcogenide is molybdenum selenide. And in that the problem with this molybdenum selenide is its poor electrical conductivity. So many materials, so many research group explored its utility just because of its structure, where electrolyte ions can easily enter into this particular material, which so that its capacitance can be higher. But the problem is its poor electrical conductivity, because its band gap is very much higher. So as its band gap is higher, the electrical conductivity is supposed to be lower. Then there is one particular what we can say interesting research what we have found is synthesizing metallic molybdenum selenide nanosheets by selective etching. That means certain layers of this molybdenum selenide is being removed by the selective etching process. And here the thing is that what we are observing is testing this in potassium sulfate as well as KCl solution. Then the CV shape what we are observing is almost symmetric. That means as it's symmetric, we can say that it is a pseudo-capacitor material compared to a battery material. That means here not that much redox peaks are coming, even though Faradic reactions are there. But the average capacitance we can take it in instantaneous capacitance we can take in each instant, so that its average capacitance can be calculated from this instantaneous capacitance, and it comes in the category of pseudo-capacitor. This was an interesting work of synthesizing what we can say metallic molybdenum selenide from this MOS2 by selective etching method. Then another research, sorry, another research also were there in synthesizing this particular molybdenum metal selenide for this pseudo-capacitor application. And again, this also proved the same. That means the utility of this metallic molybdenum selenide can give better pseudo-capacitive value compared to manganese oxide electrode. That means here the charge discharge, if we are calculating, that is here it in milliampere per centimeter square. That means here the aerial capacitance is been calculated. So it's giving a very good aerial capacitance compared to the manganese oxide. So that this metallic, what I can say that is metallic molybdenum selenide can also be a future explode area for this pseudo capacitor research. And another new material which has been emerged, that is nowadays it's a hot material we can say, is MXene. That means it consists of a max phase. Usually we can say that titanium aluminum carbide, and in that aluminum phase, that means if aluminum can be etched out, then we can synthesize a titanium carbide material, which is more of this sorts of layered stacked material. And this is having the biggest advantage of this MXene is its stability, as well as excessive sites for this particular electrolyte ions, thereby having pseudo capacitive property. See here, it's like titanium carbide MXene. So here what we can observe is like it's like a pack of cards, like ephism is almost similar to a graphene's ephism. So here if metals can intercalate into the both of these particular surface area, then the electrolyte ions can explore the higher surface area of the material, thereby increasing the capacitance. So here also we can observe that here they compare the what we can say activation of this particular material with different gases, and what they have observed is that air has hindered the particular growth, and the combination of nitrogen as well as hydrogen gas has given an improved performance compared to the other gases. Like that, this study is in preliminary stage, that how these sorts of MXene can be, the performance of this MXene can be improved for this supercapacitor application. With this MXene, again, what we are seeing is that flexible devices are also being fabricated. That means flexible MXene graphene films are being developed, and this is an interesting work. Means they tried to trap graphene into the layer between this particular MXene, and what they are saying is that uniformly the graphene couldn't be electrostatically self-assembly to this particular material. That means if suppose there are 20 layered flakes are there, only while calculating the surface area of this particular material with respect to that, they are saying that graphene could only be intercalated to only one of these 20 active sites. So in that case itself, there was an improvement in the star storage. But here what we are observing is that there is a shift in energy storage process from battery type, from pseudo capacitive to battery type. So even if CV as well as CD, if we see that shift is there, this is also another path breaking work in MXene. With respect to MXene as well as graphene, both are having high conductive material, and if both are combined together, how the result will be. That is what been studied using this particular research. Then another research also explored this thing. That means what about MXene as well as ruthenium, if they are being combined as an asymmetric supercapacitor, how the result will be. So here they have compared the charge storage with respect to ruthenium as well as titanium carbide. And the biggest advantage what they are telling with respect to MXene as well as ruthenium oxide asymmetric asymmetric supercapacitor is its voltage range. That means voltage, that is the practical voltage range for any practical device is definitely matters. So here the active voltage range for this particular asymmetric supercapacitor device is around 1.5 voltage, which definitely will increase its energy density as well as its capacitance. So this is how they have characterized that they were synthesizing this particular titanium carbide material in a carbon fiber for characterizing it as a flexible device. Then both are being characterized in carbon fiber, and they have got a very interesting result which was published in 2017. So even if like this, we can say so many path breaking research for this particular supercapacitor or supercapacitor material. So to conclude this particular topic, I can say that the material selections is an important criteria for supercapacitors. Then increasing the conductivity as well as Faradic reaction are the main research interests for supercapacitor. Graphene nanocomposites as well as MXene are the recent hot materials in supercapacitor. Even bio-waste activated carbon is also modified for improved capacitance. Then the basic research problem now lies is in improving the practical cycling of the supercapacitor. The scalable design of experiments for high yield material synthesis is also required. Before ending my talk, see, we are Malaysia's first dedicated two-dimensional materials research lab, and I just joined this lab in 2019 November, and these are our basic research focus areas. That's synthesis of graphene as well as two-dimensional material synthesis and its applications. Then we are having different research groups are working here. That's energy harvesting is there, then storage is there, then conversion are there. In that we are working in battery research, then supercap-battery as well as thermoelectric field. Then another path-breaking research what we are doing is in heat transfer fluids, like we are designing industrial nano fluids, nano lubricants as well as nano coolants available. And here our research professor has are having plenty of nano lubricant projects with him, as well as nano lubricant products are also with him. Then these are our main research focus, which is there in this in our lab. Like for supercap-battery, we are trying to synthesize single material as well as ternary nano composites using graphene oxide, metal oxides, chalconodes, chalcogenides, then carbides, etc. So many materials we are focusing on, and so many industrial collaborations also we are looking forward in near this thing, because our lab is been set up in such a manner that the university and industrial tie-up should be much more commercial rather than academic. This is what our motto is. So this is our research group comprised, I mean, research group as well as our research collaborators are this one. And this is my professor, who is the head of the department of our research group, Professor Muhammad Khalid. And for any further queries regarding research opportunities or research material doubts, etc., you can definitely reach me on this particular email ID that that's shyamk@sunbay.edu.my. I'll try my maximum to help you, any budding researchers or any researchers who are struggling with their work, etc., with any part of help if you need. With my possible limited what we can say techniques as well as this thing, if I can help you, I can definitely help you out. Then I also wish all the very best for Abhivo's consultancy, who is organizing this particular seminar, by reminding them that all great stories have a humble beginning. Thank you. Thank you very much.
Thank you, Dr. Shyam. Now we can go for a question and answer session.
Okay. So here the first question is that how can you draw equivalent circuit to your impedance graph? Usually it depends on this thing. An impedance circuit usually consists of what a capacitance, a capacitor should be, definitely should be there. Then an equivalent resistance, this thing should be there. And then what? Then what we can say, a Warburg impedance or something should be there. So firstly, if you are using what we can say, an auto lab, if you are using suppose an auto lab, then I think that will give you that particular equivalent circuit by fitting that impedance graph. Otherwise, you can use what another software is there, C-fit is there. In that we can fit that particular this thing using these this thing. That means 4 elements should be there. That will be an RS, then 2 parallel, this thing will be another resistance and another capacitor. Then one constant phase element should be there. That constant phase element only will be is used for removing what we can say, there are defects in particular electrodes. In order to remove that defects, this constant phase elements will be used. This was the question which has been asked by Ramachandran Murugesan. I hope that it's been answered. And if you are having any doubt, you can just mail me so that I can clear your doubt in better manner. Then, yeah, good morning, Dr. Preetham. Preetham is asking that which one is better, supercapacitor or supercap-battery in practical applications like high power application, which one is more advantageous, why? So according to my experience, actually the supercapacitor will be better, because usually higher power application, we require more power than energy. But there is an energy gap. That's why these particular materials, all the materials are being what we can are being searched, and in order to improve the energy density without disturbing its power density. So but unfortunately, when we are increasing the energy density, all of these materials power density is being lost. So what I feel is that supercapacitor is better for higher power application rather than supercap-battery. Then Sudhakar is asking one question. Conducting polymer and metal oxides are redox type supercapacitor. Yeah, definitely they are redox type supercapacitor. Then redox will be involved. How is first statement is true in definition? Yeah, that means here, Sudhakar, what I was telling is that there are supercapacitors are usually we call supercapacitors, EDLC supercapacitors as generally as supercapacitors. In EDLC, carbon materials are been involved. So as carbon materials are been involved, there are no redox process involved in carbon materials. That's why I mentioned that there is no redox process will be involved. Then conducting polymers as well as metal oxide comes under that category of supercap-battery, which involves redox type this thing. So redox type supercapacitor is not there. That is a misconception. Actually, redox type supercapacitor comes under battery type hybrid material, or we can say it as a supercap-battery material. Then Siddharth Nair is asking one question that I have heard that activated carbon can be used for supercapacitors. It will be eco-friendly also. So what are the challenges faced on that? Why is not that much implemented? The implementation process, it's eco-friendly carbons are only used in what we can say that commercial supercapacitors. Usually the activate carbons from coconut shells that are being used in these commercial supercapacitors. And in lab scale, when we are synthesizing this activated carbon, the biggest problem is the washing as well as chemical activation. So the biggest problem with this activated carbon is its pore size required for this particular material. So it should be in between mesoporous and microporous size. Then only proper electrolyte intercalation will be take place, and that's what this one. Actually, it is implemented. It is much more implemented in industrial scale. Then Ravi Shankar is asking, can you explain hydrothermal carbonization? Ravi Shankar, it will be better that I will answer your query through mail. If you can mail, then I can send you some papers also regarding this hydrothermal carbonization, because it's a lengthy explanation. Then there's one question from Shalu Singh from Bundelkhand University. Chance is asking that supercap-battery has low power density. So how we can enhance power density of supercap-battery? Yeah, that's the biggest research problem lies, because when we are improving the energy density, that means the intercalation of electrolytes ions is much more deeper into the material, thereby having much more what we can say time involved in this process, so that the power density will be reduced. So yeah, maybe there can be some research on MXene this thing, where that power density of that particular material is appropriate, so that some without losing its power density, we can increase its energy density can be achieved. That may be another thing. Then Preetham Bharadwaj is asking, how does the work function of an electrode affects its operating voltage window? Yeah, that's also another good question by Preetham. Actually, yeah, the work function of an electrode also affects its operating voltage window. Then why sometimes in Nyquist plot of supercapacitor semicircle isn't formed completely? Yeah, that's another good query. That means in Nyquist plot, usually in carbon, that particular semicircle is being formed, where that charge transfer process is like EDLC. And here incomplete process, that means incomplete process shows that the charge transfer process is much more pseudo-capacitive rather than EDLC. Then Sudhagar is asking, Sudhagar, which is better? And capacitance calculation can be done from CV and CD. Yeah, it is better means it's from CD only is better, because it's only determines the practical capacitance. Then what is the difference between cyclic voltammetry and galvanostatic charge discharge? Preetham, both are electrochemical characterization techniques, and the cyclic voltammetry determines whether any redox process is involved in this particular process, and what about the reversibility of the process, where galvanostatic charge discharge calculates how much time is required for charge as well as discharge. That means basically for calculating the practical capacitance, charge discharge process is being taken. Then for any application, are we connecting battery and supercapacitors together? Your thought, please. Yes, definitely there are. That means for higher power applications, that means for electric buses, etc., battery and supercapacitors will be connected together. That means for braking application, that means higher power application, supercapacitor will be used. Then similarly, if doors of that particular electric buses should be open, then there also supercapacitor will be used. And even in flights also supercapacitors are being used for door opening facility, where it is having higher power requirement is there, supercapacitor could be used. Then like so many queries are there. I think if
Shyam.
they can if they can send me mail, then I can
Fine, sir. Like so many questions are. I mean, it's getting popped up.
Yeah.
Maybe like we'll take a copy of that, and then we'll send to you through email or something like that. So that maybe you can answer whatever the questions.
Actually, it was very good that this much amount of queries are coming and everyone is interested in supercapacitor application, etc. Yeah.
Fine, sir. So like maybe we'll end up the session now. Like thank you, Shyam, for your nice presentation on the diverse aspects of materials that is related to supercapacitors. So in fact, it was like a good talk to the students and the audience community. So thank you so much for your valuable time and accepting our invitation to give this talk.
Okay, once again, once again, thank you to you. Thank you to all.
Thank you, Dr. Shyam.
Okay, thank you, sir. Thank you very much.
Thank you very much.
Thank you. Okay.
Thank you, sir. Thank you, Doctor.
Okay.
Fine, sir. Maybe then, like, maybe you can end up the talk. Maybe then we'll ask the Praveen to talk to you, sir.
Okay.
Fine.
Bye.
Fine, sir.
Bye.
Bye, sir. Thank you, sir.
Thank you.